Okay, so I would like to talk about a subject I'm interested in for several years already, namely about universal homogeneous structures. Particular examples will be Banach spaces, but I would like to survey the general theory first, some history, and then some specific results. So, how is it? Oh, okay. So, where is the outline is not so important. So, the history starts from Cantor. So, this is something very well known. The set of rational numbers, when you look at it as a linearly ordered set, is a unique countable linearly ordered set with dense ordering. So between any 2 points you find another one, and no endpoints. For every point you find something above and below. And unique means up to an order isomorphisms. So now the idea of proof, the proof is rather simple. The idea is called back and forth argument. So this is what I'm going to talk about in some abstract setting. Actually, this back and forth was developed later, after Cantor, by Huntington and maybe independently by Hausdorff. So, well, the argument I will explain later, but it's more or less you take two sets like this, you construct partial isomorphisms first from the left to the right and back. So now another thing which is completely independent, maybe not completely for sure, Urison's new Cantor's work, but this was something forgotten. This was a result of Urison, actually published after he died already, so it was not very well known. It's from a different part, a little bit different part of mathematics. So there exists a unique, complete separable metric space, unique up to isometry, with the property contains all separable metric spaces, isometric copies. One could actually say all countable metric spaces, it would be the same, but okay. And then this is an interesting property. This is what is usually called ultra-homogeneity or just strong homogeneity. Every isometry between finite subsets extends to an isometry of the full space, bijective isometry. This is called the Urison space. And next, so the main topic, the main theme is comes from a mathematician, Roland Froissart. Okay, he is known for several things, but one of the really well-known thing is the Froissart limit construction. So actually it comes from a paper from a not very well-known journal, but it was later published also somewhere else and republished in many books. So I'm going to explain the setting. This is now in model theory, okay, so it is really in logic, but you could think about specific examples. So, for example, finite linearly ordered sets, abelian groups, metric spaces. So, the setup is as follows. We start from some class of, well, I say finitely generated models, but this means just, let's forget about finitely generated, let's say finite. Could be finite metric spaces, finite linear orders, finite graphs is an important example. And now there are some assumptions. So if you have such a structure and you have a substructure, submodel of this, it should be in the same class. This was the original assumption, that the class is hereditary. Now, given two structures in the class, you could always embed it in a single structure, okay? Well, so the next thing, the third thing, this is called, I think I never wrote it in these slides, but it is called amalgamation property. This is crucial. So you have two structures with some intersection, but I didn't write it very formally. This intersection means that actually both structures from X and Y coincide on the intersection. This is what I mean that it belongs to F, that it is well defined. For example, you have two metric spaces intersecting, and the distances on the intersection are compatible, are the same from both. So you should always be able to embed both things into another structure so that it coincides on the intersection. So for example, the union can have a structure. In metric spaces, this W could be taken as the union, X union Y, and it is a standard exercise to check that you could really extend the metric on the union. It is not completely obvious, but it is possible. With finite graphs, just the union with no more edges is okay, etc. So this is the crucial thing, amalgamation property. Now, this is called a Fraisse class. Now, okay, in order to state Fraisse theorem or Fraisse theorems, because there are maybe two, we have these finite or finitely generated models. We need to speak about bigger objects, countable, infinite. So these are just unions of chains. Okay, so in case of, say, linear orders, if K is F is a class of finite linear orders, then F bar would be all countable linear orders. If this is a class of finite metric spaces, F bar will be all countable metric spaces, etc. So these are really the limits of these finite models. So now I need a notation given a countable model. There is actually standard in the literature related to Fraisse limits, that this is called the H of a model, all finitely generated submodels. And now the theorem of Fraisse is that if you have such a Fraisse class, there is this assumption. So actually one example, I'm repeating finite metric spaces. This is not good because we must have countably many isomorphic types. And isomorphism of models is really preserving everything. So for metric spaces, this would be an isometry. And there are uncountably many two-element metric spaces. But if you restrict to rational distances, this would be okay. Now, what it says, that there exists a unique model which is a countable union of these things. That is why it's called limit after. It has the property that it contains exactly models from this class, exactly these objects. And then it has such an extension property. So what does it mean? We have an embedding of a small structure, small finitely generated structure inside this. You can, and this structure is contained in a bigger one, but also in F, then you can always extend this embedding. Okay, and this extension is also an embedding. Okay. Now, actually, the main point about it is this. This, what was on the previous slide, it actually could be reformulated in this case. This is called exactly ultra-homogeneity. So every partial isomorphism between finite or finitely generated substructures extends to an isomorphism of the full one. And this U is unique, as it was written before. And it's the second property, which is called universality, of course, is that every structure in this F bar can be embedded into this. Okay, so this is this result. Now, examples that I mentioned already. So this comes from Cantor. Cantor didn't present it this way, of course, but it is indeed one case. Now, something which is called the random graph or Rado graph. Okay, this is sometimes defined as a graph with countably many vertices, which is obtained by some stochastic process. one of these standard processes gives actually the same as Frey's limit, where the class consists of all finite graphs. Now, the rational, something called the rational Urysohn space. This is of this form, where you take the class of all finite metric spaces with rational distances. If you take all distances, there is a problem of countability. There are uncountably many. But with rational, you can make it. And it turns out that the completion of this space is really the Urysohn space. This is true. Urysohn did it in a different way, but that is why I mentioned Urysohn's work, but it is really related to this. Okay, there are much more examples which I'm going to skip now. I want to mention an example from Banach space theory, which looks a little bit similar. So this is about the Gurari space. Gurari's work from '66. He constructed a separable space with, you remember this Frey's theorem, there was this extension property that you have an embedding of a finite, now these small objects, this is what plays the role of F, of the Frey's class. These are finite dimensional Banach spaces. Of course, there are uncountably many of them, continuum many, but anyway, these are the small objects, and now there exists this Banach space, this separable, which is like the completion of a countable union of finite dimensional. Every isometric embedding extends, okay, from a subspace to a bigger space. Unfortunately, there is this epsilon. The extension is an epsilon isometric embedding, and Gurari already knew that this epsilon cannot be removed. Okay. Okay, this is what I mentioned here. The Gurari space, from this condition you could prove something which I call almost homogeneity. This means that every isometry between finite dimensional subspaces extends to a bijective almost isometry. Almost in the sense that its norm is 1 plus epsilon and inverse is 1 plus epsilon. Okay, but not with isometries. And now, because of this problem, this is different with the Urysohn space. The Urysohn space, the complete metric separable space with similar properties, is homogeneous. Is this Urysohn already knew? With this one, it is not, and apparently a uniqueness which you get for almost for free from Frey's theory. You get it also for free if you have these properties of Urysohn space. For the Gurari, it was not known for 10 years. It was Lusky who proved that the Gurari space is unique up to isometry, no epsilons here. This is important. Apparently, because why I mentioned this example, I would like to point out that it fits into a general framework for treating these Frey's limits. And so there is a recent result which I have with Sławomir Solecki. It's unpublished yet. What we prove, actually this is nothing really new, because Lusky already proved uniqueness of the Gurari space, but we proved the result is not so important. The proof is important. That we proved that for every epsilon isometry, epsilon close, you will find a bijective isometry. So this of course proves isometric uniqueness, because you could take x equal to 0 and y equal to 0. So there is a unique Gurari space. But the point is that we are using some simple geometric lemma and a back and forth argument, like for the proof of Frey's theorem or Cantor's theorem, but with epsilons. So I call it approximate version. I will come back to it later if time permits. Okay. So now let's come back to the general history. I would like to not to skip too many details. So this Frey's theory was a little bit after Frey's was extended by Jonsson to uncountable cases, still in model theory. Okay. Then much later, by Droste and Gebel, it was put into the framework of category theory. Actually, their applications were still models, but they wanted to have more general embeddings. They had applications to algebra and domain theory. So domain theory is in theoretical computer science. These are certain partially ordered sets. And now, in 2006, so relatively recently, Erwin and Soletsky, they considered the classical Frise theory, finite models, but instead of embeddings, they were taking quotients. So they reversed the arrows. They call it reversed Frise theory. They found one interesting application. They got new characterization and new properties of something which is called the pseudo-arc, which is a metric connected compact space, which has some property like an arc, but it isn't. It is indecomposable, etc. Okay, now let's say I would like to sketch the category theoretic approach which I take. Droste and Gebel made assumptions which actually they really repeated this Johnson theory, but they put it in a more general context. And I started to work on this a few years ago, and I proposed the following approach. So I used the language of category theory, mostly the language only, not too many properties. No, okay, functors will be sequences only, etc. No adjoints, etc. So category theory is only the language so far, okay? But of course, you can make it much more abstract. So now the properties. So we have a category where it would be good to think that all these arrows are some sort of embeddings. Okay, because if you take some category of sets with all possible functions, everything will become trivial and doesn't make too much sense. So it's good to think that these are some sort of embeddings. And now this property means that for every two objects you find something which contains both of them. Okay. Now this what is called amalgamation. Given any two, let's say embeddings, some sort of embeddings in these arrows in this category, with the same domain, I can always close this diagram, okay, to find another one. Okay, it could be, for instance, if I take f equal to g, and this is very easy because then b equals to a and I put the same. This means like identifying points in typical examples, but this is still okay. So the assumption is general, but this is very important for having this Frise limit after. So now the crucial notion which I consider, I decided to write it in a simple way, omitting some details. So you see the sequence is countable. In Frise theory, this would be a chain of models, of finitely generated models, bigger and bigger. Now this is with respect to the arrows. So I define a notion which, as you may guess, this will lead to a Frise limit. I mean, if you take the limit of this sequence in a bigger category, this will have this property as a Frise limit. So first property is that every object embeds somewhere in this sequence. Second property is that whenever I am at some place in the sequence, I have an arrow, an embedding somewhere, I can always come back by somewhere in this sequence. Okay, this is, so there are these two simple properties. In many cases, if you have some initial object like a zero space or empty set, this could be forgotten. This will follow from this and from amalgamation. So this is the crucial thing. And now, again, I'm skipping some details. You can read this. Assume K has countably many isomorphic types of embeddings arrows. Okay, but the general assumption is dominated by countably many. This means, roughly speaking, that you could take a countable subcategory for which you make this Frise sequence, and it will be Frise in the big. But I don't want to write a definition. It's a little bit somewhat technical, but the theorem says that there exists a Frise sequence, and actually this is if and only if. Of course, the assumptions I made before are this amalgamation property, etc. Now, homogeneity and uniqueness. So I stated in the language of sequences. Actually, my idea was not to talk about the bigger category, about two categories, like finite models and countable models. I prefer to do it in this way, because all sequences also form a category. So now this homogeneity and uniqueness, it says that you have two Frise sequences, every embedding, say embedding, okay, every arrow in this category extends to an isomorphism. So if you interpret their possible limits in some category, this will be exactly this homogeneity. And also uniqueness, because you always find some arrow of this form. So this Frise sequence is unique up to isomorphism. Second thing, which is even easier to prove, is every other sequence embeds into this. And now I have to point out that these sequences are countable of length omega, okay, like usual sequences. Otherwise, it is not true. And I will speak about uncountable objects after. So now, how to visualize this back and forth argument, this very abstract one. So you have these two Frise sequences. Actually, this f goes this direction, and in the theorem was the other, but doesn't matter. You start with some arrow. Using the fact that this is Frise, the second property of being Frise gives you that you can come back. This means that this is commutative. Now you use the fact that this is Frise, you can come back with this, so that this is commutative. Then you continue, and so on. Okay, and now at limit, which is not written, okay, there is one more. All these arrows, they are compatible with this, say, you can think that these are inclusions in practical cases. That these are some sort of sets with some structures, could be some Banach spaces, for instance, and these are some inclusions. All these things, they are compatible with each other. Each Gn extends Gn minus 1. So you really have a limit in arrow, and the same for f's. So, and these two arrows will be, both compositions will be identity, right? So this shows that they define an isomorphism. This is in the very abstract setting. Okay, there was one more. Now about universality. If I want to really be in accordance with the language of category theory, I should call it weak universality, but doesn't matter. So I am given a sequence, and I have this Frise sequence. So first I find some place to embed x0. Now I use amalgamation property. Okay, so I find some objects so that this diagram can be closed. I use the fact that this is a Frise sequence, so I can come back with this. And this is how I extend. This embedding is extended to x1. And the same later. I have an embedding from xn. I make amalgamation, and then I continue. Okay, so this is how I get this embedding. If you apply it to this modal theoretic setting of Frise, it's exactly this, but it can be made in a much more abstract setting. Okay, now, okay, I wanted to mention some applications to Banach spaces. So now, before stating this, I have to say that this theory of Frise sequences, it makes sense also for transfinite length, uncountable length, okay? The problem is that you need to assume that this sequence is in some sense continuous. This was done by Johnson for models, in model theory, then by Droste and Gebel, already in category theoretic setting. But anyway, nobody knew as a byproduct of this that this is what I found a few years ago. And unfortunately, there is this assumption, continuum hypothesis, that continuum is the smallest possible. The assumption is needed because I want to know that there are Aleph-1 many isometric types of separable Banach spaces. But if this is true, if continuum hypothesis is assumed, then there is a unique Banach space of density Aleph-1, the smallest non-separable, contains isometric copies of all Banach spaces up to Aleph-1. Okay, would be enough to say all separable, then you could prove from the second property, you would be able to prove more, but anyway, all spaces up to density up to Aleph-1 and is homogeneous with respect to all separable subspaces. Okay, so what does it mean? You have two separable subspaces, and isometry between them you can always extend to a full isometry of the space. Isometries are linear, I didn't say it before. So no epsilons like with the Gurari space. And okay, I should mention that this was proved later by other people. Without this assumption, you could prove the existence, but not uniqueness. Okay, and the density will be continuum and so on. This is another story which I don't have time to mention, but it somehow was not known before. So it is a non-separable kind of strong Gurari space. And now another thing, this actually was kind of a byproduct. I thought that it was known, but somehow it wasn't. So what I was really interested in, I was working with some Banach spaces, and one of the notions which I was interested in is a projectional resolution of the identity. It's shortly PRI. So what is it? It is a sequence of norm 1 projections, transfinite, meaning that this kappa is really a cardinal, okay, and you go for alpha are ordinals below. Now the property is that the images have smaller density than the space. This is not the original definition. I just made it weaker, okay? Usually the assumption is that the density of this is alpha plus Aleph 0, okay? But this is sufficient. Now they are very compatible, meaning that if you take the composition of both, it is always the projection with the minimum. So the images form an increasing chain, but also the projections, they are compatible because you could put also beta alpha and you receive the same. So this means that you project onto a bigger space, then you use the projection onto the smaller, is the same as going directly. Okay. Now this means that all the images actually cover the space, or they are dense in the space. Is more or less equivalent, and this is there's actually natural continuity of this chain of spaces of the images. Okay, it's a little bit technical, but apparently this is the only tool for proving good properties about a Banach space by induction. You assume that these spaces have some good property, like some equivalent locally uniformly convex norm or some one-to-one operator into some C0, then you prove the same for the bigger space. And okay, some historical comment. This notion, actually, Lindenstrauss used some of this version for every reflexive Banach space has this property. And it was studied by several people, Fabian, Orihuela, Prichko, Valdivia, Zisler, and okay, probably I didn't mention anybody, all the names, but these are people who really studied this property. And now, the result, I was interested in finding a universal Banach space with this property. For example, if you ask a universal Banach space which is reflexive, this cannot exist even for some larger classes. There are some classes of Banach spaces like weakly compactly generated, which also have this PRI, and there are no universal spaces in these classes. And now if you take all spaces with PRI, assuming the continuum hypothesis, then there exists such a space. So there exists a Banach space with a PRI, density Aleph 1. It is universal, but actually in the stronger sense, complementably universal for this class of Banach spaces with a PRI. Every Banach space with a PRI with density Aleph 1 at most is one complemented. So it not only embeds, it's also one complemented after this, after some embedding. And this is actually if and only if here. And now there is this property similar to the previous space, but now this holds for one complemented subspaces. You have two separable spaces. For both of them there exists projections of norm 1 onto them. So then you can always, every isometry between them you can extend to the full isometry. Okay? There is something more technical which could be put here. Somehow this is compatible with the PRI, but okay, I'm not mentioning this. And the space again is unique. Now, I have to mention, of course, Banach spaces with PRI were studied by Professor Valdivia, and there is some class of related compact spaces which is called Valdivia compact spaces. Why this class is interesting? Because the Banach spaces of continuous functions have good properties, good renorming properties, for example. Now, what is it? So a Valdivia compact space is a space which embeds into it's a compact space which embeds into a Tikhonov cube in such a way that a dense set enters something called sigma product. Sigma product are all elements with countable support. The sigma product has good topological properties, and it allows to construct many retractions, and indeed these are the relations to the previous thing. So for a compact space of weight Aleph 1, I'm sorry, I forgot to write Valdivia compact, otherwise it cannot be true. So every Valdivia compact K of weight Aleph 1, the C of K has a projectional resolution of the identity, and here is the other statement. Yeah, again, I forgot to write PRI. Every Banach space of density Aleph 1 with a PRI has the property that the dual unit ball with weak star topology is Valdivia compact. Okay, so these are like two dual classes. However, with these Valdivia compact spaces, there is something more, that there are many retractions. So now I will write I will present the statement. So again, assuming continuum hypothesis, I could prove that the existence of this space actually implies this. Anyway, there is a Valdivia compact space K, such that every other is homeomorphic to a retract. So for compact spaces, if you think about universality, so normally it would be with respect to quotients, that every other compact in the class is a quotient. Very often universality means this, but here it is in both, because every Valdivia compact can be embedded in such a way that the image is a retract. So it's like embedding and projection. And now there is this property given, I say write invertible maps, I mean retractions, but not inside the space. It means that the range can be embedded so that it becomes a retraction. So every two right invertible maps, every homeomorphism where X and Y are compact metric can be lifted to a homeomorphism here. There is something more here related to the sigma product, but I'm not going to mention, it would be a little bit too technical. I mean, this universal Valdivia compact space has more properties, more than this, some sort of homogeneity between compact metric subsets which lie in this this dense set from the sigma product, but okay. Now, actually what historically was earlier, what I found earlier, and I realized later that it is related to Freysse limits, was this result which doesn't require any assumptions, any continuum hypothesis or something. Namely, there exists a linearly ordered compact space, which is Valdivia compact. This means that the compact space has a linear order compatible with the topology. Totally ordered, some people say, okay, linearly ordered. Such that every non-empty linearly ordered Valdivia compact space can be obtained as a quotient, and this quotient is also increasing in the sense that it preserves the orders. Okay. Okay, this is not written here, but it turns out that this k omega 1 can be regarded as some sort of a Freysse limit. You could put more properties here and making it unique, because this statement doesn't make it unique. And the weight of this compact space is Aleph 1. No matter what continuum is, it is always the smallest uncountable. It cannot be bigger. This is another theorem, that every linearly ordered Valdivia compact space has weight at most Aleph 1. And there are examples of weight Aleph 1, so the theorem is not trivial. Now, okay, I mentioned these results and these for Banach spaces, but I will not present any sketches of proofs how to obtain this. I can only say that you cannot, well, okay, at least I could not obtain it from any classical theories. I needed more tools. And actually, really, category theoretic, one construction which was first introduced by Dana Scott in lambda calculus, this is the following. You start with some category K, but now you think that the arrows of K are all homomorphisms, or all continuous functions, or all linear transformations. And you define a new category. Okay, I wanted to use some symbol, non-standard, let's say. So the objects are the same, but the arrows are now pairs, okay? So the left part of the pair is an embedding. The right part of the pair is a projection. Okay, I say embedding projection, this is the name, and this equality means that this is like, in topology this would be retraction, and embedding is right inverse. In Banach spaces this would be really projection and isometric embedding. This equality is strong enough to say this. Okay, I'm not saying what are the compositions of arrows like this, but it is obvious that you compose the left parts and you compose the right parts. The order is reversed on the right. And this is the main point here, because if we think about Banach spaces with a PRI or Valdivia compact spaces, actually they can be described in this language. And okay, these are the examples. Let's take the category of separable Banach spaces with linear operators of norm 1. Now, a Banach space of density Aleph 1 has a PRI if and only if it is the limit of some sort of continuous omega 1 sequence in this category. Okay, this is if and only if. And now this continuous, I mean that when you forget about projections, you take only embeddings, this becomes continuous. So it is not fully continuous in the category. Well, continuity of a sequence in the category would say that on every limit ordinal, the object is the limit of the restriction. This unfortunately does not happen, and that is why there are some difficulties which I managed to overcome. Okay, so with compact metric spaces with continuous maps, we have something similar. A compact space of weight Aleph 1 is the now inverse limit of some sort of continuous omega-1 sequence in this category means that we have quotient maps and also embeddings which witness that these quotients are attractions. And now, so this is how you rephrase this with this language. And now if I say sequence, I can prove that under some assumptions in this category, I have a Frise sequence which is continuous enough, and I can make this back and forth argument and everything, okay, obtaining these results, which does not fit into the results of Droste and Gebel mentioned before, or not. It's not model theoretic anymore. So this is it. Now, I think. Don't know at what time exactly I should finish, so I want to discuss only some further topics which I didn't write any details. So, and what I can do with this projection embedding pairs, what is possible to do is to construct a complementary universal space with a basis, but this, for instance, with some Schauder basis of length omega-1, but you need to consider more subtle category, okay? But this is not written yet, but this is possible to obtain. And well, another thing is to consider Banach spaces of bigger density, of course, but this is another thing. Now, I wanted to discuss, I finally decided that the details are a little bit technical, approximate Frise limits. So, unfortunately, there is no blackboard, but anyway, the idea here is that I consider a category like finite dimensional Banach spaces, because this is the canonical example, or Urison space, which is better understood. So actually this is more important. And now some embeddings are isometric, some embeddings are almost isometric. So for each, say, arrow, you can define some sort of a norm of the arrow, okay, and some measure which tells you how far it is from an isometry. And then all these things which I presented before, this Frise sequence and this back and forth argument, you can do considering diagrams which are not commuting, but they are epsilon commuting, okay, where epsilons tend to 0. And this is what I was doing, finding this simple proof of the uniqueness of the Gurari space. It is not written in the language of categories, but in the spirit of categories. So there are some very natural axioms which you can put to obtain, as a particular case, this thing as some sort of approximate Frise limit. And for free, you get uniqueness up to isometry, etc. I didn't mention that the old proof of the uniqueness of the Gurari space by Lusky, it involved some very non-trivial results of Lazar and Lindenstrauss on representing matrices. So it was far from being simple. Now I would like to apply this to, for example, there is a space, complementary universal space with a Schauder basis constructed by Pełczyński. Nobody thought about its isometric uniqueness. Isomorphic uniqueness is easy, but I think it can be applied, and perhaps to some other cases. Finally, the last topic, which is actually in progress, joined with Antonio Aviles from Murcia, is what we consider Frise functors instead of sequences. And now functor, actually the domain, sequence is a functor whose domain is, let's say, the set of natural numbers of the set of ordinals up to omega-1. We consider some functors whose domain is some sort of a partially ordered set or even a lattice. And we are able to get homogeneous objects, okay, homogeneous universal in some sense of very large density, weight, size, or whatever, and no assumptions like continuum hypothesis, nothing like that. And also in particular some Banach spaces. For example, non-separable Courari space, which is in some sense unique. It's made non-separable Courari in the sense that it's stronger than Courari without epsilons. Okay, but it has the property like Courari, but we're omitting the epsilons. So this can be done. And well, I didn't write on the slide, but there is another thing why all this theory is interesting is that even in the classical setting, recently, a few years ago, there was some interest in the groups of automorphisms of Freisel limits, that they have some interesting properties from the point of view of topological dynamics. So I'm sure that there is a lot to be done because this could be put to a more general picture. Okay. So I think I will finish with this. I just put some references. I mentioned works of other people, so here I mentioned this, what I have still preprint. This is the main thing what I was talking about. The universal Banach space with a PRI is contained in this recently published book. Some related subjects are here, and this short proof of uniqueness of the Courari space is mentioned here. So I think that's all what I wanted to say. I hope it's not too long, not too short. So thank you for your attention.